Okay, good morning. I want us to have a look at a topic in Form 4 known as electrochemistry. Electrochemistry. So, electrochemistry is defined as a branch of chemistry that deals with the relationship between electrical energy and chemical reactions. Relationship between electrical energy. Oh. Yeah, yo, sawa.
So nothing utatuambia jina, unaenda kufunzwa ni class gani,
Oh, sawa.
then sasa tunaweza 3, 2, 1.
My names are Mr. Sunguti Albert from Bosco Secondary School. I'm going to teach Form 4 topic known as electrochemistry. Electrochemistry is defined as a branch of chemistry that deals with the relationship between electrical energy and chemical reactions. The relationship between electrical energy and chemical reactions. So we can say it is a branch of chemistry. It is a branch of chemistry concerned with the relationship between electrical energy and chemical reactions. The relationship between electrical energy and chemical reactions. This relationship between electrical energy and chemical reactions, it is discussed in two parts. There are two parts that are concerned with this electrochemistry. The first one is whereby some chemical reactions are used to produce electrical energy. Chemical reactions are used to produce electrical energy. A typical example of such a case is whereby we look at the cells that we use in our simple electric appliances. We also have the lead acid accumulators that we use in the car batteries and so on. There are some chemical reactions that take place within those cells which produce electrical energy. That electrical energy can be converted to various forms that are useful to man. The other part is whereby electrical energy is used to cause chemical reactions. Electrical energy is used to cause chemical reactions. A case of electrical energy being used to cause chemical reactions is an example of electrolysis. Electrolysis, whereby when you pass an electric current through an electrolyte, a decomposition reaction occurs. For instance, in Form 2, you discussed electrolysis of binary electrolytes. Electrolytes that are made of only two elements, a metal and a non-metal. And in the process, we found that when an electric current is passed through that molten electrolyte, a decomposition reaction occurs, producing a metal and a non-metal on the other side. Those are the two cases that this topic is mainly concerned with. So, we have said that there are two parts. One is where chemical reactions are used to produce electrical energy. 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 And two, how the same electrical energy can cause chemical reaction. Electrical energy causing chemical reactions. Electrical energy causing chemical reactions. And with this, we have said we are going to look at electrolysis. So, to begin us off with this, we are going to look at what we call a redox reaction. Redox reaction. As the name suggests, redox. Red is the short form of reduction. This part represents reduction, and this part represents oxidation. So, redox reaction simply means a reaction in which both oxidation and reduction occur at the same time. A reaction in which both oxidation and reduction occur at the same time. Such a reaction where we have both oxidation and reduction occurring at the same time, we say it is a redox reaction. There are various definitions of reduction and oxidation. So we need to come across to remind ourselves of a few of those definitions before we go to the main item that we are going to discuss today. So we can form a comparison table for the same reduction and oxidation. We can see the differences by using a comparison table. Reduction is defined as the removal of oxygen from a substance. Removal of oxygen from a substance. The removal of oxygen from a substance is reduction. The addition of oxygen to a substance is oxidation. Addition of oxygen to a substance, that one is oxidation. Another definition of reduction is the addition of hydrogen. Addition of hydrogen to a substance, then removal of hydrogen from a substance. Removal of hydrogen from a substance. That one is oxidation. Another definition for oxidation is loss of electrons. Loss of electrons is oxidation, and gain of electrons is reduction. Gain of electrons is reduction. The other definition and last one, which will stand as a building block for this topic, is oxidation is the increase in oxidation number, and reduction is the decrease in oxidation number. Reduction is the decrease in oxidation number, and oxidation is the increase in oxidation number. Reduction is the increase in oxidation. Gain of electrons, that is reduction. Loss of electrons, oxidation. Decrease in oxidation number, reduction. Increase in oxidation number, oxidation. Those are the main definitions of reduction and oxidation that we are going to dwell on. We can remind ourselves of reactions, redox reactions, whereby we involve oxygen, we involve hydrogen, and electrons. Let's take an instance of zinc solid reacting with copper 2 oxide. Zinc solid reacting with copper 2 oxide. It's going to give us copper, zinc oxide, and copper metal. So in this case, we say that zinc has gained oxygen. Therefore, zinc has been oxidized. This process is oxidation. Then copper 2 oxide, oxygen has been removed from copper 2 oxide. Oxygen has been removed from copper 2 oxide. Therefore, this process is reduction. So you can see there is oxidation and reduction in terms of oxygen. Let's have another one where we have hydrogen being involved. So we have this one, copper 2 oxide, reacting with ammonia gas to produce copper. We have nitrogen gas and water. Copper, nitrogen gas, and water. Copper, nitrogen gas, and water. In that question there, you find that oxygen has been removed from copper. Oxygen has been removed from copper. That one is reduction. But again, we see that ammonia has been oxidized to nitrogen gas. Hydrogen has been removed from ammonia. When we remove hydrogen from ammonia, we obtain nitrogen gas. That process is oxidation. That is where hydrogen is involved. Let's have the third case whereby we are having gain of electrons or loss of electrons. And with this, I'm going to write a full equation for the electrolysis of molten lead 2 chloride. So this one is going to give us lead metal and chlorine gas. Lead metal and chlorine gas. And you find here that from lead ions to lead metal, it means electrons have been gained. When the lead ions gain electrons, they form lead metal. When the chloride ions lose electrons, they form chlorine gas. So here, electrons have been lost, that is oxidation, and here electrons have been gained, this one is reduction. So those are the cases whereby we have oxidation and reduction in terms of oxygen. The other one is nitrogen and hydrogen, and then we have in terms of transfer of electrons. Now, with the oxidation number, we have talked of increase in oxidation number. We are going to consider a reaction between copper 2 sulfate solution. I have copper 2 sulfate solution here, which I am going to react it with some reducing agents here. I have iron powder and I also have zinc metal. So I'm going to do two experiments, two demonstrations on the same to see what happens when iron powder is added to a solution of copper 2 sulfate solution. A solution of copper 2 sulfate. Iron powder is added to a solution of copper 2 sulfate. So I have added some iron filings to the solution of copper 2 sulfate. You can see that the color of the solution changes from blue to pale green. The color of the solution changes from blue to pale green. It changes from blue to pale green. And there is a brown solid. There is a brown solid that is deposited at the bottom of this reagent bottle. You can see a brown solid at the bottom of this reagent bottle. A brown solid at the end of this reagent bottle. Now, this indicates that the brown solid that is formed here is copper metal, and the pale green solution, a green solution that has been formed there, is a solution of iron 2 sulfate. Therefore, the reaction is we have iron reacting with copper 2 sulfate solution. This one will produce iron 2 sulfate solution and copper metal. Iron 2 sulfate solution and copper metal. The color of copper 2 sulfate is pale blue. The color of iron 2 sulfate is green. The color of copper metal is brown. The iron filings or the iron powder you have seen is gray. So the observations that are made here is the iron when it's added here, the pale blue color of copper 2 sulfate changes to green. Then there is a brown solid that is formed there. If we can derive an ionic equation from here, we can see that here iron reacts with copper 2 ions in solution to produce iron 2 ions, and copper metal. Produce iron 2 ions and copper metal. So you see, from iron to iron 2 ions, that is, electrons have been lost, and from copper 2 ions to copper metal, electrons have been gained. So here, where electrons have been lost is oxidation, where electrons have been gained is reduction. We can also have another one, whereby we use zinc powder. Zinc powder. I have zinc powder here with me, which I can also use to demonstrate the same. So I'm going to take a small amount of volume of copper 2 sulfate, and this zinc powder, you can see, is gray. So I'm going to add some zinc powder here in this copper 2 sulfate solution. I'm going to add zinc powder in this copper 2 sulfate solution. So with the zinc, I'm going to stir the mixture using a glass rod. I'll stir the mixture using a glass rod. I'll stir the mixture using a glass rod, and then I will allow it to settle so that we can see whether there is a change in color in that solution, and then also be able to account for that change in color of the solution. That change in color of the solution. Let me add some more. Okay, as we wait for the reaction to proceed to completion, let me write the ionic equation for the reaction that will take place there. So that is zinc powder, solid, reacts with the copper 2 sulfate solution. That is going to give us zinc sulfate solution, and copper metal. The ionic equation, of course, is zinc reacting with copper 2 ions to give zinc ions in solution, and copper metal. So also here, the zinc is gray, the copper 2 ions is pale blue, the solution of copper 2 ions is pale blue, zinc ions are colorless solution, and copper metal is a brown solid. So here, you see that from zinc to zinc ions, electrons have been lost electrons. So this one will use the oxidation part. From copper 2 ions to copper metal, electrons have been gained, so that will be the reduction part. So in the process of the same thing there, you realize that there is both oxidation and reduction in the event of these two solids being the two solids, that is iron and copper 2 sulfate reacting, then zinc and copper 2 sulfates reacting. In both cases, we have seen that there is transfer of electrons from the metal to the metal ions that are in the solution. Transfer of electrons from the metal to the metal ions that are in the solution. So, when electrons are lost by an atom of an element, the oxidation number of that element increases. When electrons are lost, the oxidation number of that element increases. That is, when electrons are gained, the oxidation number of that element decreases. So that brings us to the question of what is this oxidation number? What is this thing we are calling oxidation number? Yeah? Oxidation number or oxidation state is defined as the apparent charge of an element. The apparent charge of an element. The apparent charge of an element. This apparent charge of an element, for you to arrive at that apparent charge, there are 6 main rules that should be observed when assigning oxidation numbers. 6 main rules that should be observed when assigning oxidation numbers. 6 rules. 6 rules. Number 1, the oxidation number of an uncombined element or neutral molecule is always 0. The oxidation number of an uncombined element or neutral molecule is always 0. That is, If we have an element like zinc, the way it has been here, iron, the way it has been there, magnesium, sodium, hydrogen molecule, oxygen gas, nitrogen gas, molecules as they are, such that they have not combined with any other element, their oxidation numbers are said to be 0 because the number of protons is equal to the number of electrons. Therefore, the overall charge in these substances is always 0. Number 2, the oxidation number of a monoatomic ion, that is an ion of one atom of an element, is equal to the charge on that ion. So, like if I have magnesium ion like that, magnesium ion as it is, it will have an oxidation number of positive 2. If I have nitride ion, as it is here, the oxidation number of nitrogen is said to be negative 3. We can have zinc. Zinc ion, the oxidation number of zinc is positive 2. So if we have an ion of one element, an atom of one element, the charge on that ion is equal to the oxidation number of that element. Number 3, the oxidation number of nitrogen, not nitrogen, oxygen. The oxidation number of oxygen in most compounds that contain oxygen is negative 2. The oxidation number of oxygen in most compounds containing it is negative 2, except in peroxides where it is negative 1 and oxyfluorides where it is positive 2. For instance, if I want to find the oxidation number of oxygen in a compound like water is negative 2. The oxidation number of oxygen in a compound like hydrogen peroxide is negative 1. And if we have oxyfluoride, the oxidation number of oxygen is positive 2. That is rule number 3. So the oxidation number of oxygen here will be negative 2, here is negative 1, and here is positive 2. Number 4, the oxidation number of hydrogen in most compounds containing it is positive 1. Oxidation number of hydrogen in most compounds containing it is positive 1, except in metal hydrides where it is negative 1. Water, the oxidation number is positive 1. I can say sulfuric 6 acid, oxidation number of hydrogen is positive 1. But if I have like lithium aluminum hydride, the oxidation number is negative 1. Sodium hydride, the oxidation number of hydrogen is negative 1. Remember, hydrogen can be placed in either in group 1 or group 7 because it can gain 1 electron like group 7 elements, whereby when it gains 1 electron, it will form a charge of negative 1, or group 1 elements where it loses 1 electron to form a charge of positive 1. Number 5 and 6 are very, very important rules. Number 5 says that the sum of oxidation numbers of all atoms in a compound must be equal to 0. All atoms in a compound is equal to 0. So by that we mean if I have a compound such as water, let me use water as an example. If I have a compound such as water, water has 2 atoms of hydrogen and 1 atom of oxygen. The oxidation number of 2 hydrogen atoms plus the oxidation number of 1 oxygen atom cumulatively should give us 0. Sulfuric 6 acid has 2 atoms of hydrogen 1 atom of sulfur and 4 atoms of oxygen. So the oxidation number of 2 atoms of hydrogen plus oxidation number of 1 atom of sulfur plus oxidation number of 4 oxygen atoms together should give us 0. That statement can be used to find the oxidation number of any element in a compound. Number 6, and lastly, in case of radicals, you know that a radical is a group of atoms with a net charge which exist and react as a single unit. Now, in case of a radical, the overall charge on the radical is equal to the sum of the oxidation numbers. The overall charge on the radical is equal to the sum of the oxidation numbers of all atoms in the radical. That is, if we have a nitrate ion like this, the nitrate ion is made of 1 atom of nitrogen and 3 atoms of oxygen. So this implies, therefore, that the oxidation number of 1 atom of nitrogen plus the oxidation number of 3 atoms of oxygen, together, when we add, we should get -1. We have another radical. We can give an example of phosphate. 1 phosphorus atom, 4 oxygen atoms. When we put together that, we should get an overall charge of -3. We can use that to find the oxidation number of any element. Like, let's say, for example, let's look for the oxidation number of phosphorus in this radical phosphate. So we want the oxidation number of P. So we are going to say P plus, we have 4 atoms of oxygen. But then using rule number 3, we see that this phosphate is not a peroxide, it is not an oxyfluoride. Therefore, the oxidation number of oxygen is -2. So 4 times -2. This one should give us the overall charge, which is -3. By that, if we can do some algebra there, 4 times that will give us -8 is equal to -3. So P will be equal to -3 plus 8. This one gives us +5. Remember, for oxidation number, we have to put the sign, we have to include the sign. We don't just write it as 5 like that. Yeah, mathematically, 5 there is correct. But this is a charge. Oxidation number is charge. So the positive has to be included. Let's look at another example. Find the oxidation number of chlorine. Find the oxidation number of chlorine in these 2 compounds. Find the oxidation number of chlorine in these 2 compounds. And then I can have another one like that. So let's start with the first one. The oxidation number of sodium. Sodium, as it is here, it is going to be +1. We are looking for the oxidation number of chlorine. Chlorine, we can assign it a value X, or let's just use the same symbol, chlorine. The oxidation number of 1 atom of sodium, +1, 1 atom of chlorine, we don't know, plus the oxidation number of 3 oxygen atoms, 3 times -2. This one should add up to 0, since this one is a compound. The sum of all oxidation numbers should add up to 0. So +1 plus chlorine plus -6 should give me 0. +1 plus -6, it will give me -5. This one is equal to 0. Then chlorine, we find it is +5. So the oxidation number of chlorine in this one is +5. What about this one? Potassium, +1. Oxygen, we know, since it is 1 atom, it is going to be -2. Plus that chlorine, 1 chlorine atom, should give us 0. So +1 plus -2 will give us -1, plus chlorine is equal to 0. So chlorine is going to be positive 1. So oxidation number of chlorine here is positive 1. Oxidation number of chlorine here is positive 5. I will preserve these examples because in our next item, we are going to look at how we can use these oxidation numbers. So it brings us to uses of oxidation numbers. There are two main ways in which oxidation numbers are useful. Two main ways in which oxidation numbers are useful. One, oxidation numbers are useful in keeping track of electron movements in the course of a chemical reaction. Keeping track of electron movements in the course of a chemical reaction. The substance whose oxidation number increases, it means electrons have been lost from that substance. As I said previously, that when a substance loses electrons, then the oxidation number increases. If the oxidation number decreases, it means electrons have been added to that substance. If I may go back to one of the ionic equations we did at the beginning, this one is going to give us copper metal and zinc ions. So you realize that the oxidation number of zinc here is 0. Oxidation number of copper is positive 2, since copper is a monoatomic ion. Then here 0, then here positive 2. So in terms of oxidation numbers, the oxidation number of zinc has increased from 0 to positive 2. That shows electrons have moved from zinc to copper ions. Because when electrons are removed, the oxidation number increases. Here, the oxidation number of copper has decreased from positive 2 to 0. So from that, keeping track of electron movements in this reaction, we can conclude that electrons have come from zinc and gone to the copper ions. So by using the oxidation states, we can be able to know which substance has gained electrons, which substance has lost electrons. Keeping track of electron movements in the course of a chemical reaction. And since we can be able to see that there is a decrease in oxidation number and an increase in oxidation number at the same time, then we can call it a redox reaction. The other use of oxidation numbers is nomenclature. They are used in IUPAC nomenclature. IUPAC nomenclature of compounds. IUPAC nomenclature of compounds. Especially compounds of elements that have got more than one valency. More than one valency or more than one oxidation state. Compounds of elements that have got more than one valency or more than one oxidation state. That is, we can use oxidation numbers to name those compounds. For instance, this one we have seen in this compound here, the oxidation number of chlorine is positive 5. Therefore, we can say that this compound is called sodium chlorate 5. Sodium chlorate 5. This one here is sodium chlorate 5. Sodium chlorate 5. Sodium chlorate 5. It shows that this 5 shows that the oxidation number of chlorine is positive 5. This one, we can call it potassium chlorate 1. Potassium chlorate 1. Potassium chlorate 1. Potassium chlorate 1. Potassium chlorate 1 indicates that the oxidation number of potassium in this compound, of chlorine, not potassium, the oxidation number of chlorine in this compound is positive 1. But their common names exist. This one is called potassium hypochlorite. That's a common name, potassium hypochlorite. This one is sodium chlorate. Sodium chlorate is a common name. But the IUPAC name is not sodium chlorate. It is sodium chlorate 5. So we can use the oxidation numbers to give the names of compounds, especially compounds of elements that have got more than one oxidation state. Compounds of elements that have got more than one oxidation state. Examples of other compounds, we can say copper 2 oxide, copper 2 oxide. We call it cupric oxide, copper 2 oxide. We have iron 2 sulfate, iron 2 sulfate. Iron 2 sulfate is called ferrous sulfate. Ferrous is the common name, ferrous sulfate. But when we say ferrous sulfate, iron 2 sulfate means that the oxidation number of iron in this compound is positive 2. So we can use oxidation states or oxidation numbers to name compounds of elements that, especially those that have got more than one oxidation state. Compounds of elements that have got more than one oxidation state. Therefore, now we are able to know, we are able to tell whether a reaction is redox by looking at the oxidation numbers. By looking at the oxidation numbers. So let's see something here. As we conclude, let me use one of those ionic equations, or I may change and give another one. Aluminium reacts with iron 2 ions. Since aluminium is more reactive than iron, it tends to displace iron from a solution containing its ions. So these are 3, 2, 2, 3 there. So a redox reaction, we have said that there is oxidation and there is reduction. In any redox reaction, there is oxidation and there is reduction. And as such, we can identify, go further and analyze that redox reaction. We observe that there is something that undergoes oxidation. The substance that undergoes oxidation, the substance which is oxidized, is called the reducing agent. The substance which is reduced, or the substance which undergoes reduction, is called the oxidizing agent. So oxidizing agent, the substance which is reduced is called oxidizing agent. So you find that in any redox reaction, the oxidizing agent gains electrons, the oxidizing agent gains oxygen, the oxidizing agent gains hydrogen, loses oxygen, and gains electrons. That is the oxidizing agent. It becomes reduced. The reducing agent becomes oxidized. So it means in this reaction here, the reducing agent is aluminium reducing agent because it becomes oxidized. Its oxidation number increases. The reducing agent is iron 2 ions. The oxidizing agent is iron 2 ions. Why? Because its oxidation number decreases from positive 2 to 0. So today we have discussed electrochemistry as a branch of chemistry that deals with the relationship between electrical energy and chemical reaction. We have said that relationship is discussed in 2 ways. One is where there are chemical reactions that are used to produce electrical energy, that is in cells, and also where electrical energy can be used to cause chemical reactions. We have looked at the redox reaction, the aspect of a redox reaction, and said that a redox reaction is a reaction in which both oxidation and reduction occur at the same time. We have tried to give a comparison between the oxidation and reduction in terms of oxygen, in terms of hydrogen, in terms of the electron transfer and the oxidation numbers. We have also seen how the oxidation numbers are assigned, rules that are required in assigning oxidation numbers. We have also used the same and seen how the oxidation numbers can be used to keep track of electron movements in the course of a chemical reaction, as well as the way we can use oxidation numbers in naming compounds, using the IUPAC system. We have said that in a redox reaction, oxidation takes place, that is, there is one substance which is oxidized. The substance that is oxidized is the reducing agent. In other words, the substance whose oxidation number increases is the reducing agent. There is also one substance which is reduced, that is, it undergoes reduction. The substance whose oxidation number decreases, because reduction is a decrease in oxidation number. The substance whose oxidation number decreases is the oxidizing agent. So we shall continue by looking at displacement reactions in our next lesson. Do have a good day.